Hey guys, welcome to System Design in Minutes, where we break down scalable systems in a relatively short amount of time. Today, we're going to build a URL shortener. Although this video is structured like a system design interview, we're going to keep it relatively high-paced so that you can benefit from it regardless of if you're a beginner or even if you have slightly more experience and you just want a quick refresher before an interview. Let's start with our functional requirements. Our first requirement should be that it should be able to shorten a long URL and that it should be able to redirect the user from a short URL to a long URL. We're going to keep analytics, TTL, and custom aliases out of scope of this system design. So with that out of the way, let's dive into our non-functional requirements. First, we need to figure out how many read requests we're going to be getting per second. Let's assume that we're going to have 100 million monthly active users, where each user creates 10 links each. That means that we're going to be getting about 500 write requests per second and 5,000 write requests per second with a 10x peak multiplier. So now that we know how many write requests we're going to be getting per second, let's figure out how many read requests we're going to have to handle. If you think about it, URL shorteners are very read heavy. If one person creates a link, about 1,000 more people open it. We can assume that our read to write ratio here is going to be 1,000 to 1. If we get 500 write requests per second, we're going to be getting about 500,000 read requests per second. And if we get 5,000 write requests per second in peak times, we're going to be getting about 5 million read requests per second during peak times. So with these assumptions out of the way, let's think about how much database storage we're going to need. So if our database looks something like this with the links in a users table, we can expect our total storage requirements to be about 175 gigs. It's important to note that this number is just for a single database node and it doesn't take replication into account. Moving on, we need to figure out if we need to prioritize availability or consistency. I would argue that for a URL shortener, we need to value availability over consistency because it's fine if users see slightly stale data or face some replication lag, but it's much more important for them to have a fast experience and see a response no matter what. With that out of the way, our fifth requirement should be that our redirection speed should be very fast. And to quantify that, let's say that it should be less than 200 milliseconds. We don't want our users to be sitting in limbo in our redirection page waiting for their original URL to open. And our last requirement should be that our shortcode for our short URL needs to be as small as possible, and it needs to be unique. Now the question is, how small does it need to be? We're going to figure that out at a later stage when we think about how we are going to generate a shortcode. With our non-functional requirements done, we can move to our API design. This is going to be very simple. We're going to have a post route called /shorten, which is going to take a long URL. This is going to go to the server, and our server is going to generate a short URL for this and save it in the database. Our next route is going to be a get route called /shortcode. When this route hits the server, it fetches the long URL associated with the shortcode and it returns a redirect 301 or 302 response to the user. We can have a discussion about if 301 or 302 is more appropriate. A 301 is basically a permanent redirect and 302 is a temporary redirect. A 301 is cached in the browser and CDNs. So when you first send a GET request and you get the redirect response, your browser might cache it, and the next time you go to it, your browser might automatically redirect you to the original URL without ever having to visit our services. That's great, unless you have an endpoint for updating the long URL associated with a shortcode, or if you actually want all the GET requests to hit your server for analytics. In that case, a 302 would be more appropriate. But for our use case, a 301 works perfectly. So now let's talk about how to generate a shortcode. There are multiple ways to do this, but we're only going to be discussing two ways in this video. The first one is hashing, and we're going to be discussing the second one at a later point in this video. With hashing, you take a long URL and you pass it through a hash function like SHA-256, which gives you a 256-bit binary, which is obviously too long, and with just ones and zeros, it will be impossible to generate billions of combinations while keeping the URL short. We take the 256-bit binary and we base 62 encode it, which gives you a shortcode a little above 40 characters consisting of small a to small z, capital A to capital Z, and 0 to 9. But 40 characters is still too long. To fix this, we can just take the first 6-7 digits of this 40-character shortcode and use that. But how many do we exactly need? Well, in a base 62 encoded shortcode, just 3 digits would give us 238,000 different possibilities. 4 digits will give you 14 million, 5 will give you 916 million, 6 will give you 56 billion, and 7 will give you 3 trillion. For our use cases, 6 digits is perfectly fine. The downside of this approach is that you can have collisions, meaning if you take the first 6 digits of this 40-character shortcode, it might be that it already exists in the database. So every time you add something to the server, you would have to send a request to it to ensure that this shortcode doesn't exist. But what if it does? Well, if it does, we can just use a sliding window approach to take 6 digits from the second character instead. So this obviously works. It's not the best approach, but we're going to be working with this right now, and we're going to be seeing a better approach, which is slightly more complicated at a later stage. So with that out of the way, let's get into our high-level design and deep dives. So let's start simple with a client, a server, and a database. If the client sends a post request to the server generates a shortcode, checks if it's unique or not by querying the database, and if it isn't, it regenerates the shortcode and repeats the process until it finds a unique one and then saves it to the database. If the client sends a GET request, the server fetches the original URL associated with the shortcode from the database and returns it back to the user with a redirect response. Now, the immediate problem is that a single server won't be able to serve so many requests each second. We can solve this by having multiple instances of the server backed by a load balancer, which distributes the traffic across these servers to make sure that none of them are overloaded. But now the issue is that if we host all of it in the same availability zone, if for whatever reason that zone goes down, our website goes down as well. So we spread this entire setup across multiple availability zones. I'm not going to go too deep into how requests would get routed to the server in the closest availability zone, just to keep things simple, but for now, we have prevented our server from becoming a single point of failure. Now let's have a look at our database. We have the same issue here. Not only can a single database fail to handle so many read requests per second, but it's also a single point of failure right now. So if it goes down, everything stops working. We can fix this by introducing a primary database for writes and multiple read replicas for handling read requests, which we spread throughout different availability zones. When the server tries to add something to the database, it writes to the primary databases, and then the data gets asynchronously written to all the read replicas in the background. This might introduce some replication lag, but since we value availability and speed over consistency, that's fine. Now, the read replicas also help us distribute the load, and if one replica goes down, the others keep working, keeping our systems up and running. But now we have a different bottleneck, which is the write database, which is the primary database we're going to use for writes. We can solve this by having a standby database that stays in sync with the primary. Since we are only going to have one or two standbys, the delay caused by writing to them synchronously is a trade-off we can accept to prevent any data loss. If the primary fails, the standby can be promoted, ensuring we have minimal downtime. This way, we have redundancy not just for reads, but also for writes, making our system more resilient end-to-end. Since our system is heavily read-oriented, it would also make sense to opt for a microservice architecture and separate the servers into dedicated read and write services. This allows each service to scale independently based on its own workload. For example, if the read traffic increases tenfold while writes remain the same, we can simply add more read servers without unnecessarily scaling the write servers. We can implement this using an API gateway which forwards the requests to the appropriate services. Now that our system is relatively fault tolerant, let's look at a different problem. Imagine Taylor Swift drops a new album and shares the link using our URL shortener. Millions of people would be requesting the exact same shortcode, causing our database to be queried over and over again for the same piece of data. To solve this, we introduce a Redis cluster as a cache. We set its eviction policy to least recently used and set the short URL and its corresponding long URL in a key value pair. Whenever a GET request comes in, the server first checks whether the shortcode exists in Redis. If it does, we immediately retrieve the original URL from the cache and return it to the user without ever touching the database. If it doesn't, we query the database like we did before, cache the shortcode along with its corresponding long URL in Redis, and return the result to the user. The first request for a shortcode hits the database and is comparatively slower, but every subsequent request is served directly from the cache, significantly reducing the load on our database and making things orders of magnitudes faster. What eventually ends up happening with this setup is that most frequently accessed URLs, like the URL for Taylor Swift's new album, gets cached, and when Redis hits the assigned storage limit, it evicts the URLs that have been used the least. But Taylor Swift has fans all over the world. If someone in Japan or South Korea makes a GET request, they'd still have to travel all the way to our servers hosted, say, in the United States. That adds unnecessary latency for users who are far away from our infrastructure. To solve this, we introduce a CDN that caches our redirects at edge locations around the world. Now, whenever a client makes a GET request, it first hits the nearest CDN edge. If the redirect is already cached, the CDN immediately returns the redirect response without ever contacting our servers. If it isn't, the request is forwarded to our origin servers, which fetch the long URL, return the redirect, and allow the CDN to cache it for future requests. This not only reduces latency for users around the world, but also significantly reduces the amount of traffic reaching our servers. At this point, our system looks pretty good. except for one thing. Every time we create a new short URL, we have to make a round trip to the database just to make sure the generated shortcode doesn't already exist. But what if we could guarantee that collisions never happen? To do that, we need a completely different approach for generating shortcodes. For this, we'll introduce a distributed counter. When a write server starts up, it requests a unique range of IDs from this distributed counter. If the counter is currently at 1, the first server receives 1 and increments the counter by 999,999. When the next server requests a range, it receives 1 million to 1,999,999 and so on. Since the counter is updated atomically, no two servers can ever receive the same range of IDs. From this point on, whenever a write server receives a post request, it simply takes the next unused ID from its range stored in its memory. Since every server owns a unique range, collisions are impossible, so we no longer need to query the database before saving a new URL. Once a server exhausts its range, it simply requests another block from the counter. The only downside is that these IDs are sequential, making them very easy to predict. If someone discovers one shortcode, they could write a script to potentially guess the next few. If this is an issue, we can prevent this by passing each ID through a feastal cipher to obfuscate it. But the output from this is very long, so we base 62 to encode the result to produce a short URL-friendly shortcode before storing it in the database. With this approach, we've completely eliminated collision checks while keeping our shortcodes unique, compact, and difficult to predict. We can make the global counter using a Redis cluster, but Redis can run into split brain moments, where two instances of a write server can end up with the same range of IDs. To prevent that, we can use something like etcd, which uses a quorum-based algorithm to prevent this from happening. At this point, we are pretty much done, but we can improve this to safeguard our systems from attacks. Let's say we have a malicious user who's sending us millions of fake GET requests. Since these are fake requests, it will bypass our CDNs, hit our servers, bypass our Redis, and hit our database, which would increase our loads. To prevent this, we can use rate limiting at our API gateway and use a Bloom filter in our system to prevent fake requests from impacting our systems. A Bloom filter is just a small data structure that never gives false negatives, but it can, however, give false positives sometimes. So some of the fake requests might still hit us, but with rate limiting and Bloom filter, we can project most of them from affecting us. And with that, we've not only satisfied, but also exceeded our functional and non-functional requirements. I think this is a good place to stop. Anything more than that feels kind of over-engineered, although there's a lot of improvements you can make. I hope you learned something from this video, and I'll see you in the next one. Bye.